Welcome. In this video, I would like to show you a couple of examples of how to use the substitution method to solve recurrences. So let's start with a recurrence. Before we solve this recurrence, let me raise some issues. So for one, very often in a recurrence, we might have a theta here. But that makes it challenging to use the substitution method because it messes up our base cases. So let's assume we don't have that. Actually, we should really assume that we have the recurrence very precisely stated. That means here we will want to know how we're rounding. So if I don't say anything else, let's assume I'm rounding down, and we should also know what our base cases are. So let's assume that those are simple base cases. Let's say b for, so we at least need a base case of n is 1. So let's assume that's exactly what we have. We have a b for n is 1. And for n larger 1, we use a recurrence. So now we have our recurrence precisely stated. Now we can solve it. And the first step in the substitution method is guessing the solution. So for this recurrence, you could guess the solution using recursion trees. You could guess the solution simply because even the master theorem applies, and you'd immediately see that t of n is of order n squared. But when we use the substitution method, we want to avoid O's. So the claim that we're going to prove is that t of n is more or less equal to c times n squared for all n, and that then implies that it's an O of n squared. So we should be using a specific c here, but we'll have to figure out in the proof what the c is, and then afterwards we can simply write it here and pretend that we always knew it. This will now also be our induction hypothesis, but without the quantifier. So simply t of n is smaller equals c times n squared, but not for all n. Again, we still need to figure out what c is. We want to show this first for the base. So what is the base cases, or what are the base cases that we need? Very often that simply corresponds to the base of our recurrence. So here we only have n is 1. Sometimes we need more, and I will have an example of that later. But here n is 1 is enough. So we need to show that the induction hypothesis holds for n is 1, meaning I have to show that t of 1 is smaller or equal to c times 1 squared. So t of 1 is b, and b is smaller or equal to c times 1 squared, or smaller or equal to c, if, okay, we simply need to pick c larger or equal to b. We'll be able to still pick c, so this will work out. Now let's do the induction step. So in the induction step, we will go, and now we're using strong induction, so we will go from all values smaller than n to n. So we're going to assume that the induction hypothesis holds for all numbers smaller than n, and what that means is if I plug in, instead of n into the induction hypothesis, a number smaller than n, then I assume that it holds, and then I want to prove that this statement then also, so t of n smaller equals c times n squared, holds for n itself. And here I just wrote that I'm going from smaller n to n. You don't need to write that. So we start now simply with t of n, plug in the recurrence, use the induction hypothesis, and see where we end up. So now n half is smaller than n, so we can use induction hypothesis here. That means that we were going to replace t of n half by what we get when we plug in what we have in the induction hypothesis. So that means there are c times, and then instead of the n, because we had t of n, and on the other side n squared, now we have t of n half, so we replace n squared by n half squared. I did an extra tiny step here, namely I omitted the rounding down because I'm doing upper bounds. It's fine if I remove those, because then my number just gets even bigger. So as an upper bound, that is perfectly fine. Let's see what that gives us. So n divided by 2 squared is n squared divided by 2 squared. So now we have here a term 2 times c divided by 2 squared. So that is simply c half. And then if I take n squared outside, I get the following. I get c half plus 1 n squared. Now what I would like to have here, that t of n smaller equal c times n squared. This we need to guarantee. So when is this the case? It is a case if c divided by 2 plus 1 is smaller equal c. So when is that the case? Let's see. So we need that c half plus 1 is smaller equal c. We can bring the c half to the other side. Then we have 1 is smaller equal c half. So we get that 2 is smaller equal c. Now we can pick c. So now we're going to say that c is the maximum of b and 2. And with this, the induction goes through. Let's have a look at another example. So let's have an example with several base cases. So it's easy to get an example with several base cases if the recurrence simply has several base cases. But here's an example where the recurrence only has one base case, but still we will need several base cases. And why will we need several base cases? The issue here is that we'll want to prove that t of n is smaller or equal c times n log n. And now we have the problem that log of n for log of 1 is 0. So let me show that. So we're going to prove that t of n is smaller or equal c times n log n for, okay, c I still need to specify, but we can only prove this for n larger or equal 2. And the reason for this is the following. Assume we would want to prove it also for 1, for n is 1, then we would get something of the type t of 1 is smaller or equal c times 1 log 1. But if I have a 1 and the log, so this will be simply 0. So I want to show that 1 is smaller or equal 0, and that won't work out. So I cannot prove the claim for t of 1, for n is 1. So we're going to start with n is 2. And that will result in more base cases. So let's start with the base case n is 2, because that we will definitely need. But let me first state my induction hypothesis, which we want to prove then also for the base case. So the induction hypothesis here again is simply the claim without the quantifier. So now let's do the base case n is 2. We will want to have that t of 2 is smaller or equal c times 2 log 2. So what is t of 2? So we use the recurrence. We get 2 times t of 2 divided by 2, so t of 1. 2 times t of 1, that's 2, plus n is 2, so 2 plus 2, that's 4. And that should be smaller or equal c times 2 log 2. Now log 2, that's 1, so we simply have c times 2 here. 4 smaller or equal c times 2 is true as long as c is larger or equal to 2. So if c is larger or equal to 2, we have this. Now we would like to handle all other cases with the induction step, but we can't. And why can't we? So what is the problem with n3? So the problem with n3 is if I have a 3 here and I use first the recurrence and then want to use induction hypothesis, if I plug in 3 here, I get t of 3 divided by 2, rounded down, that is t of 1. But t of 1 is nothing where I can apply the induction hypothesis, because the induction hypothesis I can apply only when n is at least 2. And for good reasons, because plugging in 1 here is not a good idea. So 3 is a case which would be based on 1, and because 1 is not a base, we need to make 3 a base. So we need to make sure that n of 3 smaller equal c times 3 log 3. So we want to have that 5 is smaller equals c times 3 log 3. Now we already know that c has to be at least 2. And if I have c at least 2, on the right hand side I have 2 times 3, that's 6, times log 3 is even larger than 6. And if c is larger, it's even larger. So we are already fine. That handles the base case. Now we're ready to do the induction step. So in the induction step, we assume that the induction hypothesis holds for all numbers smaller than n, and then need to prove that it also holds for n. So let's write down the assumption. All numbers smaller than n, but of course larger or equal to, because that was where we started. So now we want to prove that the induction hypothesis also holds for n. So for that we start with T of n, use the recurrence, use induction hypothesis, rewrite the expression, and hope we're done. So n half is smaller than n, so we can apply the induction hypothesis. We do so by taking n half and plugging it into the induction hypothesis. So instead of c n log n, we get c n half log n half. We can omit the rounding down because without rounding down, we just make the expression larger and we're doing upper bounds. Also note that this now indeed goes through for 4 because 4 divided by 2 is 2 and we have that 2 is larger or equal to 2, so that is perfectly fine. Now what we have here is we have a 2 and a 2 that cancel. So we have c times n log n half. Now log of n half can be rewritten as log of n minus log of 2. Now log of 2, we always do logarithm base 2, so log of 2 is actually 1. So we have c times n log n minus c times n times 1, so simply c times n plus n. What we wanted to have actually is that T of n smaller equal c times n log n. So what we want to have is the following. Now I'm only allowed to write this if it's actually true. So when is this true? It's true if minus cn plus n is smaller equal 0, because then indeed the left hand side is smaller equal to the right hand side. So we need to have that minus cn plus n smaller equal 0. As long as c larger equal 1, this is the case, because then I have minus cn, which will be more than n, plus n that's negative. And with this, I conclude the induction step. Now I just need to actually choose my c. I need that c is at least 1. I need that c is at least 2. If I set c to 2, that fulfills both of these conditions. And I'm done. I want to give you one more example. And the reason for this example is that in this example, the natural induction hypothesis does not quite go through, and we need to add a lower order term to make it work. Let's see this. Now, you can first guess a solution. You can use the recursion tree. You can use here also simply the master theorem. That will tell you that T of n should be in O of n. So that's what we want to prove. T of n is in O of n. The natural induction hypothesis would be to say T of n smaller equals c times n. So why does this not work? Let's simply try it. And let me immediately do the induction step to show where the problem is. So we would start with T of n, use the recurrence, use the induction hypothesis. So we plug in n half into the induction hypothesis. Now 2 and 2 cancels. We have c times n plus 1. So now we wanted to prove that this is smaller equal c times n, because that is what the induction hypothesis says. So that is what we want to prove for n. But this is only the case if 1 is smaller equal 0. 1 is not smaller equal 0. So this cannot work. So if you end up in a situation like this, you will observe that there is a lower order term here. Lower order term here means that we have the dominant term c times n, and then there's a term of lower order which gets into our way. We can handle this term by simply having a term of that order in the induction hypothesis. So I will have a minus d in the induction hypothesis, and I will still need to pick these constants c and d. And what c and d will be, that will come out of the proof, the base cases, and the induction step, and then I will simply set these numbers. So let's do that. We start with the base case. The base case here is simply n is 1. So what we want to have is that 1 is smaller or equal to c times 1 minus d, and that is the case if, let's say, d plus 1 is smaller or equal to c. I could have also simply said this is a case if 1 smaller or equal to c minus d, same statement, but this gives me a relation between d and c. We will use that later. Now the induction step. We assume that the induction hypothesis holds for all numbers smaller than n. We now want to prove that it also holds for n. We start with t of n, use the recurrence. n half is smaller than n, we can apply the induction hypothesis. Now be very careful that if you have a lower order term, then you need to make sure that you also use it in your induction. That means in the base case, here we have to also have the d. We cannot simply work with c. Also in the induction step, here, if I plug in n half, because the induction hypothesis has this lower order term, it has to be here. In this case, plugging in n half into c times n minus d simply gives me c times n half minus d. Again, I omit the rounding down. Now let's rewrite this. The 2's cancel, but only the 2's in the c term, not in the d term. So make sure to have the 2 there. And now we want that this is smaller or equal c times n minus d. So when is that the case? So we have c times n on both sides. So here is a minus 2d, here's a d. So if you compare those, on the left-hand side we have a minus d plus 1. So we need to have that minus d plus 1, that is smaller or equal to 0. Then we get this. And this is the same as saying that d should be at least 1. Now we can plug this in. So we simply pick d as 1. Now we needed to have that c is at least d plus 1. So at least 1 plus 1. So if we pick c as 2, everything goes through nicely. So now we've proven the induction hypothesis, and this also gives me the asymptotics that I want to have. So let me just write this explicitly. So given that t of n is smaller or equal to 2n minus 1, we know that it's in O of n. And this wraps up this proof. This also wraps up this video. Thanks for watching.